So welcome back to the rest of the research day. This is Victor Zhong. He's a new Vector faculty member. He has just joined us this academic year. We're very, very happy to have him here. He is also a professor assistant professor in the David Sheridan School at University of Waterloo. His research is on efficient machine learning methods that interpret language to generalize new problems. He'll be talking about generalist language agents in general purpose operating systems. Welcome.
All right, thank you for the introduction. So I'm a new professor in Waterloo. I'm part of the Reading to Learn lab that I lead. You can find more information about it online. I want to talk to you today about some of our work on building generalist agents in general purpose operating systems. So the research question that we have is, how can we build these generalist agents so that they can find information for you online, they can schedule calendar events for you from emails, for instance, or scaffold your slide deck, or draft your reports. So how can we build this agent that is able to work with multiple applications to solve a diverse selection of tasks that require diverse strategies in diverse situations? So today's talk will kind of go through two areas of this work. The first one is about how can we build a test bed for developing these agents, and the second one is how can we efficiently train these agents. So first we'll talk about test beds. Due to the time limit, I'm not going to go into previous work in a lot of detail, but here are some kind of main constraints of existing work. So a lot of the existing work, such as code generation, so things like SWH bench you might be familiar with, or things like Spider, WikiSQL, they have to do with code generations. And these are a really kind of fundamental challenge in machine learning, but at the same time, they are single modality. So they only consider things like text-to-text generation, for instance. Another body of work are multi-modality, like web shop, but they're limited to single tasks. So in the case of web shop, you are looking at a screen, maybe a website, as well as instructions, and you're trying to help users shop for items online. Another body of work is on multitask, but they have to do with single applications. So these are things like Web Arena, where you have these agents that have to perform tasks on things like Reddit or GitLab to manipulate these websites, but these tasks don't require these agents to reason about multiple applications at the same time. And this is something that we do as humans in our everyday use of our computers. The final group of work are things like mind-to-web. So here, we do consider using multiple applications at the same time. These are web applications, so you might have to do Google search and then go to a website, identify some sort of form, complete it, and so on. But a lot of these environments, such as mind-to-web, they don't consider interactions, and instead they only consider demonstrations. So these benchmarks are not able to allow us to develop things like exploration strategies, because the agent has to essentially complete the task the same way a human would during some ground truth demonstration. So the first work I want to talk about is OSWorld. This is a work led by Tian Bao at Hong Kong University. This creates the first real computer environment designed for the development of multimodal agents. So in OSWorld, we have a task instruction in language. We also have the initial state setup that includes a virtual machine, for instance, Ubuntu or Windows, as well as popular applications like Excel, Chrome browser, VS Code, and so on. And also, we set up the GUI stage, so some intermediate stage in the operating system. Once we have this initial setup, we drop the agent into OSWorld, and the agent observes raw screenshot input as well as text accessibility trees. And the goal of the agent is to complete the language instruction by operating the raw keyboard and raw mouse control. Once we have the action from the agent, OSWorld executes this control in real time. And at the end of the interaction trajectory, we evaluate the semantics of the final state.
Excuse me, sorry. When you're saying the observation or the environment, the agent will see or they get feedback, the raw screenshot and the text, right?
The text is the accessibility tree from the text menus.
Okay.
Yeah, so for visual impairment, for instance.
Okay. Thank you very much.
So how is OSWorld different from prior work? Well, first, it supports multiple modalities. It has screenshots and text accessibility trees. It supports multiple tasks. So using file management, web applications, coding via VS Code, Office applications like Word, Excel, PowerPoint, email. And also, very importantly, it's executable and it has semantic evaluation. This means that the agent can explore and discover alternative strategies And this is crucial for generalization in the real world because you can't hope to obtain perfect coverage of the evaluation setup with your training demonstrations. So in total, OSWorld has 369 real-world tasks mined from online tutorials, YouTube videos, computer forums, and so on. And the very important thing is that these are naturally existing information intent, naturally existing instructions and questions from real users. They're not artificial tasks designed by the authors. Second, we carefully construct initial states to simulate the fact that when you use your computer, you often start from some intermediate state in the operating system. So you're not rebooting your computer every time. And finally, we spent a lot of time designing the evaluation. So this is to measure, did the agent actually complete the task? Is the final state correct in the semantic sense? Not that they perform the same sequence of actions that some human performed during a Go demonstration. So just to reemphasize the amount of effort that went into this, this is more than 400 man-hours of writing evaluation code, doing 4 rounds of checks to verify that the instruction is reasonable and the evaluation is correct, as well as things like wrangling orchestration of virtual machines. And this is really the first realistic and unified testbed to develop generalist agents in general purpose operating systems. So how does state-of-the-art models do? So we experiment with a large number of open source and closed source models. I'm just showing 3 here. We won't go into too much detail, but one observation is that these models perform very poorly. So you can see the peak performance is about 11% task completion rate. Another very interesting finding that we have is that visual models don't actually perform that well. So you would expect that a VLM is able to perform better than an LLM because it sees the screen, which has more information. But we find that VLMs don't actually have precise understanding of the screen. And therefore, it's essential to have text information for the models of today. Ultimately, we want to build towards more precise VLMs. So these red bars are GPT-4o looking at text input, for instance. And just to give you an idea of how humans perform, so the blue bar, these are the same plots. I just added the human performance on there. The blue bar is performance of computer science students who have not participated in the design of this benchmark. They're at about 72%, which is vastly better than where the foundation models of today are at. And there's more analysis on our paper. You can either Google OSWorld or you can go to os-world.github.io to see our website. Okay, so we talked about test beds. The next part I want to talk about is how do we train generalist agents? And the 2 works I want to mention here are learning from feedback. So first we'll look at learning from human feedback, and second we'll look at learning from automatic feedback. So let's look at learning from human feedback. So suppose we have this policy learning setting. So we have a robot arm. We start with some policy. So maybe this is a random policy. Maybe this is a worm started policy. And we have some task. So maybe this task says, push the chair to the marked position. In typical policy learning, we have our environment, which includes this robot and its surroundings. And then we write down some reward function. And then we can use something like reinforcement learning to improve the policy. And then finally, we get the policy in our simulator, and then we take out the code, we install it on a robot arm, and then we can use it in the real world. What is hard here a lot of the times is actually specifying the reward function. So what are some good signs that the robot is pushing the chair to the marked position, for instance? So it could be that you say, well, the chair is getting closer to the position, therefore we get positive reward, but maybe the chair is flipped upside down. So there are a lot of situations that you have to consider. And also we have to consider this for all sorts of different language instructions. So in general, it's very hard to build a general purpose reward function like this. The second work I want to talk about is textual work. So instead of manually specifying the reward, here we automatically generate an executable reward program. And the way we do this is we condition on the language goal, and we condition on an abstract interface of the environment. So the left-hand side, apologies, a bit small, but the left-hand side is an example of this, where we have an abstract Python class definition of the environment, which consists of our chair and our robot. And then for the chair, we have a property called pose, as well as an API called get point cloud distribution. And then for the arm, we have states like the coordinates of the arm and so on. So given this abstract class representation and the instruction, we show that we can use language models to generate executable reward functions. One such example is in the middle. This reward function says things like, if you are close to the chair, if your arm is close to the chair, That's good because it means you're about to push the chair. And it's bad if you start to tilt the chair over. So empirically, what does this do? So when we do this, we find that we can generate reward functions that perform similarly to human-designed reward functions. So on these graphs, the blue curves are human-written Oracle reward functions, and then the green curves are zero-shot generation using text reward. The orange ones are few-shot in-context learning with text reward. This is on the dataset many skills 2. This is just showing that the policies that we learn from text reward do sim to real. So they transfer onto real-world manipulation using this robot arm. The other thing I want to mention is that in addition to generating the reward function, it turns out it's trivial for us to interactively improve it. So consider this very naive setting where in Majoko we have an ant and we say we want this ant to lie down. So we use text reward, generate a reward function, learn on it. We have a policy, we roll it out. And as a human, we look at the ant and we see that it's upside down. So what we can do is we can say, okay, it's good, but I want the ant's torso to be top down, not bottom up. We can take this language feedback from the human, incorporate it into the instruction for the large language model, also condition on the previous reward function and have it update the reward function. And then when we train on the new reward function, we observe that the ant has the correct orientation. Empirically, we have results on challenging tasks in manipulation. So this is a specific one called Stack Cube Interactive. And here you see the top tab is zero-shot performance. Let's just look at the few-shot performance. Again, the blue curve is Oracle reward function. We see the first time we do text reward, we get flat performance. That's the purple line. Once we show the behavior to a human, they update with feedback. We update the reward function, train on it. We have the green curve after after 2 iterations of text reward. And then after 3 iterations, we have the orange curve, which is now at Oracle level performance. So learning from human feedback is great, but at the same time, foundation models today come with a lot of prior knowledge about the world. The next work I want to talk about asks the question of, can we tap into that knowledge to provide feedback to improve policies? So how does this work? So like text reward, here we start with our base policy. We roll out our policy, and then we present parts of it to our foundation model for feedback. So what does this look like? So suppose the task is we want to put 2 candles in the drawer. So we can extract a chunk from our rollout, and then we can tell the foundation model, okay, so before we started this segment, you opened some drawer and then you didn't see anything, and you closed the drawer, and then you put a candle in the drawer. Which part of this do you think was a good idea if what your goal was to put 2 candles in the drawer? And the LM will say, well, step 28, in this case, the part where you put one of the candles in the drawer, that was good. The other parts I'm not sure about. So we're going to use this insight that foundation models can identify good behavior in retrospect to update our policy. Before we do that, though, we don't want to query LLMs like GPT-4, for instance, every step, for a 1,000-step trajectory. So what we'll do first is we're going to collect some trajectories and then query for feedback using our foundation model. And then we'll use that as a data set to distill into a feedback model. And this is a small feedback model that we can run that's very efficient and fast. So essentially this feedback model, which is this yellow box at the end, it considers the history of interactions, and it tells you if the most recent interaction is productive or not. So now we can start to deploy this model. So during deployment, we're going to again start with our base policy that's here. We're going to roll it out, and then we're going to query our feedback model. And the feedback model is going to identify, okay, here are the steps that you did that I think were good. And then we're going to collect this as a data set of desirable behavior, and then we're going to imitate this using our base model to improve it. So at a high level, this technique involves verbalizing your environment such that it's interpretable by a foundation model such as LLM. Once we verbalize, we can collect feedback, and then we can use the feedback to identify good behavior, and then we can imitate that good behavior. So in this work, we apply this technique to 3 different environments. We saw an example before in an interactive kitchen or interactive house. This is an example which is primarily visual. This is navigating Google Street View in New York City. This is a fairly long pricing task. So we show an example of using multimodal models like CLIP to convert this panorama into an egocentric language description of the scene. So you can imagine that the trajectory of navigation by the agent, which is inherently visual, is now a sequence of text descriptions. Once we do this, we can use our model to provide language feedback and do policy improvement. So on all three environments, we observe that using LFM, which is language feedback models, consistently improved policy. So we are already working in this warm start setting. So we start with a state-of-the-art policy obtained from imitation learning from demonstrations. Those are the gold bars. When we do language feedback model learning on the training environments, we observe some gains. And this is a little bit surprising because the demonstrations already provide gold demonstrations on the training environment. But nevertheless, we observe some gains. I think the more important story is that once we deploy these models, we are able to go to the test environment and identify good behavior automatically and do adaptation there. And when we do that, we see fairly substantial gains, which are the final dark red bars. The gray bars here are zero-shot GPT on policy. So you can see that the foundation model, if you just wanted to act, it's a fairly difficult requirement, but it's able to provide feedback in retrospect. So I think this work is really interesting because it not only shows that we can improve with very naive use of feedback, but it shows we can extract all sorts of feedback from foundation models. So in addition, we can ask for why an action is good, we can ask for a summary of agent behavior, and we can ask for strategic areas of improvement. So I think an open question going forward is how can we tap into this knowledge in the form of open feedback and then learn from this open feedback. So I think in the interest of time, I'm not going to go over the summary. We talked about testbed, and then we talked about learning from feedback, both human and language. Finally, I just want to talk about my lab at Waterloo. So our research is centered around how can we use language to make machine learning more efficient and more generalizable. Efficient here meaning needing less supervision, less labels, less human interactions to perform well. These are things like learning from feedback. And generalizable meaning building systems that work well in the real world despite not having a lot of data for it during training. So these are things like OSWorld and these kind of efforts. And that concludes my talk. Thank you.
So if you have any questions?
Yes.
You mentioned before that visual models are worse compared to language models.
Yeah.
But that's kind of
Surprising.
counterintuitive, right? As human, we have a lot of information,
Yeah.
like the visual fields in our eyes.
Yeah.
So do you have any insight why is this the case? Is it because of the model is not good enough?
Yes. Yeah, I think in the limit, obviously we expect visual models to perform better, right? Because there's less information loss. But I think the fact of the matter is the visual models of today don't really understand precise visual inputs. So you're able to tell this is a picture of a cat that's wearing a top hat, but you're not able to tell this is the precise GUI layout of this scene. So we even have methods that try to do OCR on the screen and tag the corresponding visual parts of the image. And those models will perform kind of on par with text models even. So I think we're maybe, one thing that we hope from this development is that we push people to consider this more. But I think currently one limitation I see is this use of visual tokens, which are these general purpose kind of segmentation of your visual kind of units, if you will. And that already, because it needs to be general, it doesn't really capture precise use cases like what we're trying to do here.
It looks like using Ubuntu most of that's it.
Yeah.
It's the case that you're looking at the device logs as opposed to just the videos. By device logs, I mean like everything going on the operating system. Do you use that?
That's a good question. I don't think we collect everything in the OS because that's really big. We do have some work on collecting demonstrations that I didn't talk about right now, but primarily that's has to do with the current application that's open. So we track things like UI state, for instance, the actual video, as well as the text accessibility trees will sometimes give you some hidden states that's not available visually, but we don't try to extract every state from the operating system. That said, I think this is inherently reproducible because we're in a VM. So I think we might be able to reproduce a lot of the latent system states. Obviously, VMs are not exactly entirely reproducible either, like background processes, for instance. So I think that's a good question, but I think logistically it's very difficult.
Wonderful talk, but I was curious, for the self-correction, do you compare against just generating several reward functions and ensembling them versus self-correction? I know there's some work saying that depending on domain, sometimes just drawing more samples works better.
Yeah. We don't actually do that. I would assume that's probably the case, but we don't do any ensembling here. Oh, by the way, these works are all recently published. So the textual word was presented at iClear last year, and then the other two, the language feedback models and OSWorld, will be presented at NeurIPS in Vancouver this year. So you can always approach us at you can email me. I'm at Vector, but also we'll be talking about that at the conference as well if you're there. Any other questions?
And for the text reward, you are mentioning like the text reward, and you will kind of condition on the previous interaction, like history, and then do the next iteration to training.
When we're iteratively improving the reward function, yes. Yeah.
So it will, so the prompting will be very kind of very accumulate very long. It would accumulate a little bit, but you're not going to show the first iteration, right? So if you're doing iteration 4 to 5, you're not going to show iteration 1. So it doesn't, it's not unbounded in that sense. I mean, although we're at like 128,000 tokens right now for the limit anyway, so I think practically it hasn't been a problem so far. I think it's more of a problem when you want to do feedback learning because you want to give as much of the trajectory as you can to the feedback model, and there you could always run into limitations because of how rich the perception space is. Yes.
I noticed that in OSWorld, the undergraduate human performance rate was 72%.
Yeah.
I was curious, why are they only getting 72%?
Because we have like step limits, and sometimes these tasks can be somewhat complicated. There's an analysis of like infeasibility in the paper.
Maybe one more.
Okay.
Yeah, go ahead.
Yeah, further questions, you can always-
I usually try to approach this problem as a planning problem. For example, doing like a
You know OSWorld?
yeah, like as a planning problem, like have a reasoning tree and or graphs, and then you try to find which one is the one that's most promising and so on, and then you execute.
We are about to do that, but for this paper, no. This
Okay.
paper was just kind of establishing the baseline of foundation models.
Okay.
Maybe with things like chain of thought, and
Yeah.
there's actually some related work here of another NeurIPS paper that we'll show is called Spider 2V, which is professional tool usage, so like Snowflake, Jupyter notebooks, those kind of things. That work we do more sophisticated reasoning because the performance otherwise is even worse. But these are we've built the benchmarks, and now a lot of our research now is methodology going forward.
Interesting. Thanks.
Awesome. Yeah, feel free to reach out to me if you have more questions.
Thank you very much.
Thank you.